All right, kids, we are looking at section 4.6 with approximating with local linearity. Now, local linearity is the concept of if you graph a graph and you pick a point and you zoom in close and closer and closer and closer, zoom, 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 to that point, like I'll use this graph right here and talk about that. If I start zooming into that, this is a curved graph. But if I zoom in a million times, it's going to look like a little straight line. And so what happens is I can figure out what's going on or approximate what's going on at that point by using the tangent line. Because you see, if I zoom in on both of those together, the tangent line and the point, the graph, they're calling this point A, by the way. If I zoom in close enough, they've got a lot of similarity in this little window right here where I can estimate off the tangent line what A is doing. That's called local linearity. Now, the idea with us is tangent lines. We know tangent lines. They're calculus. We can figure out the equation of a tangent line. And if I can figure out the equation of a tangent line, then I can approximate what this curve is doing right there at that point A. That's the idea. Zoom in, zoom in, zoom in, and you've got both of them looking like straight lines that are really similar to one another. So a tangent line of the function f of x at x equals a can give you an approximate value of f of x, the function, for a point close to a, x equals a. This is a picture of something that's called concave up. It's like a smiley face, happy. This guy over here to the right, he's concave down, he's sad. Oh, so sad. If I pick a point on him and make a tangent line for him, by the way, I can pick my point anywhere. And that was very crooked. Good thing I've got a erasable pen. Here it is. There it is. Now, something that comes up with these is whether your estimation is an over approximation. Is it bigger than it actually is? Or is it an under approximation? Is it smaller than it actually is? And so for this, any time that you're concave up, it's considered to be an underestimate. And the reason why is because your tangent line's below the curve. It's an underestimate. You're going to get a value that's smaller than the actual value. Where over here, where your tangent line's above the curve on concave downs, all concave downs are going to be overestimates. It's going to come up in the problems that we do. All right, number one. F is concave up on its domain. F of 4 is 5. F prime of 4 is 3. What's the estimate for 3.8 using local linear approximation? Now, when you see these words, local linear approximation, it's code word. It's the code word for tangent. Find me the tangent. Find me the tangent line. And you say, I can do that. I've been doing that for a long time now. So in order to find the equation of a tangent line, you need a point and you need a slope. All right, go back to your words here. F of 4 is 5. Well, that's a coordinate. That's giving you the point, 4, 5. F prime of 4, that's the slope, the derivative at 4 is 3. Cool, that makes it easy. All right, so I am going to then take this thing and put it into the equation of a tangent line. So that's going to be y minus 5 equals 3 times x minus 4. You've seen that before. So far that's it. That's good. Now they're going to tell you, all right, now use that equation of the tangent line to estimate what the function's doing at 3.8. So we're going to take that 3.8 and plug it in for the x value here and see what comes out. So y minus 5 equals 3 times 3.8 minus 4. Let's calculate it out. 3.8 minus 4 is a negative 0.2. Y minus 5 equals 3 times a negative 0.2. Y equals, I'm going to bring that 5 over, negative 0.6 plus 5 gives me a value of 4.4. So that means that f of 3.8 equals approximately 4.4 based off of the tangent line. All right, then it says, is it an overestimate or an underestimate? So go back to the wording of the problem. They told you, they gave it away right here. They said it's concave up. You say, all right, well, if you're concave up, you're an underestimate. So we say there's an underestimate. And they want an explanation because f of x is concave up. Now, in other words, this is a little smaller than the actual value would be. So 4.4 would be a smaller value than the actual value. And we'll talk more about that in example number 2. Here comes example number 2. This time they give us an equation. All right, so the way that they're giving us the information is a little bit different. However, our process is going to be the same. Here's my function, concave down at x equals 1. Find the tangent line. All right, so here I go. I know I need a point. I know I need a slope. Now, my point is going to be 1 something, right? My x value is 1. I don't know what that something is. Well, how do you find the something? So I am going to plug a 1 into my function to figure out what the y value is. 5 times 1 minus 2 times 1 cubed minus 2. And so I work my way through that, and lo and behold, I get a value of 1. There's my point. My slope, they didn't give me slope either, but my slope comes off the derivative. Can you figure out the derivative? So my derivative would be 5 minus 6x squared. Is that right? 5 minus 6x squared. Okay, so my function is here. I just took the derivative. What do I have to plug in? An x of 1. 5 minus 6 times 1 squared is a negative 1. So there's my slope. Put it together. Y minus 1 equals negative 1 times x minus 1. Then that's it. They want me just to find the equation of the tangent line. There it is. What is the estimate for f of 1.1 using the local linear approximation for f at x equals 1? What do? You find the tangent line, you plug in an x value of 1.1 and see where it comes out. So here I go. Y minus 1 equals negative 1 times 1.1 minus 1. A whole lot of 1s. Y minus 1 equals, if I distribute out negative, if I take 1.1 minus 1, I get 0.1. 0.1 times negative 1 is a negative 0.1. Swing the other 1 over, again, lots of 1s, I get 0.9. Is it an underestimate or an overestimate? Go back up here, concave down, tangent lines are above. That means it's an overestimate. Overestimate. Explain. Because f of x is concave down. Now, just for kicks and giggles, I went ahead and plugged in 1.1 into the original function. When I found f of 1.1 in the actual function up here, plug it in, 1.1, 1.1 cubed, yada yada. Guess what popped out? 0.838. So you can see, yeah, it really is, 0.9 is close, really close, but it is an overestimate. It's a little bit larger than the actual value would be. So kind of neat that you can put all those pieces together. All right, last one, number 3, last example that is. Consider the differential equation. You got it there. Let y equal f of x be a particular solution of the differential equation with the initial condition f of 2 equals 0. Write an equation for the line tangent to the graph of f at the point 2, 0. Well, they were nice to us. They gave us the point. The point is 2, 0. Thank you very much. So I only need to figure out what the slope is to come up with that tangent line. Now, to come up with the slope, what you're doing is you are finding the derivative and then plugging the derivative, plugging your value of x is 2, y is 0 into the derivative. But look at what they gave you. Like, be very careful of the things that they're giving you. The last one they gave you f of x. Look what they gave you this time. They gave you the derivative. And so since they gave you derivative, all you need to do is do direct substitution of x is 2, y is 0. So here's what it's going to look like. E to the 0, parentheses, 2 times 2 squared minus 5 times 2. X of 2, y of 0. E to the 0 is 1. 2 squared is 4. 4 times 2 is 8. Minus 10. And so I get a negative 2. Write an equation of the tangent line. Here I go. Y minus 0 equals negative 2 times x minus 2. Most times we don't leave the 0 there, but however you want to write this thing. There's a lot of different equivalent forms. I'm going to get rid of the 0 and distribute the negative 2, negative 2x plus 4. That is my equation for my, excuse me, for my tangent line. Now use it to approximate 2.2. Well, where does that 2.2 go? It goes in for the x. So here I go. If I approximate it, now I'm y equals negative 2 times 2.2 plus 4. And that gives me negative 4.4 plus 4. Gives me a value of negative 0.4. There it is. Bam. Linear approximation means find the tangent line. Plug it in. They're going to be really similar answers. So I'm going to pick a few practice problems. First one is number 3. Number 3. Let me find my number 3. Here it is. I picked this guy because it's a trig function one, and I know y'all love your trig. All right. Answer the questions for each function listed. My function is 2 cosine of x plus 1. It's concave down on the interval between 0 and pi over 2. Sorry about the puppy barking. He's been barking all day. All right, what's the estimate for f of 3 using local linear approximation? Find the tangent line for f at x equals pi over 2. Give an exact answer. They don't want us to round it. All right, we can do that. So I need a point, tangent line. I need a slope. For the point, they tell me x is pi over 2. Got to find the y. Go back to the original function. 2 cosine of pi over 2 plus 1. So I go to the unit circle. I think of the unit circle. Pi over 2 is up at the top. That has a coordinate. I'll put it here. Pi over 2 has a coordinate of 0, 1. Okay. Cosine is the x value. That means that this is 0, which means that you get an answer of 1. Your slope comes from the derivative. Well, they didn't help me out there at all, did they? But I can find the derivative because I am that smart. I have 2 cosine of x. The derivative of that would be, derivative of cosine is negative sine. So my derivative is going to be negative 2 sine of x. The derivative of 1 is 0, so that's it. That's my derivative. What's my x value? Pi over 2. Negative 2 times the sine of pi over 2. Well, I have that coordinate up at the top there. The sine is the y value, which is 1. So I have negative 2 times 1 gives me negative 2. Do I have enough to put my equation together? And you say, yep, you do. You got a point, you got a slope. Y minus 1 equals my slope of negative 2 times x minus pi over 2. There's my tangent line. What did they want there? They want more. They want to know what is it to approximate f of 3. So I'm going to go to my x value here and I'm going to plug in a 3. Here it comes. Y minus 1, negative 2. I have a 3 minus pi over 2. And they want me to say what that y value would be. So let's think about that for a minute. If I've got y minus 1, distribute this negative 2, it would be negative 6. Actually comes out kind of nice. Check it out. Negative 2 times negative pi over 2 is positive. 2's bang bang out of there, and I got a pi. Swing the 1 over. Here's my final best answer without rounding of a negative 5 plus pi. Then they say, okay, well, is it an overestimate or is it an underestimate? Go back to the beginning of the problem. It's concave down. Where are your tangent lines? Concave down's unhappy. Tangent lines are above. So you are going to say it is an overestimate. Explain, because f of x is concave down. There it is, number 3. All right, next one's number 5. Next, number 5. I just kind of picked a hodgepodge here along the way. Number 5 is my next one, and this one, same thing. My function, you can see the function, it's a square root, it's concave up on its domain. What's the estimate for f of 1.9 using local linear approximation for f of x equals 2, round to 3 decimal places. So for this one, as soon as you see the code word for local linear approximation, you're thinking, find me the tangent line. So same thing goes, I need a point and I need a slope. All right, so here goes my point. If I figure out, I know it's x equals 2, right? So now I got to find the y coordinate. This one becomes a negative square root of 4 minus, gosh, the dogs in my neighborhood are all going crazy. Can you hear them? 4 minus 2. And so I'm looking at that and I'm going, oh man, did they really do that to me? And they did. They gave me a negative square root of 2. That's your y coordinate. That is not so pretty, but that's okay. We can handle it. Now the slope comes from the derivative. Now I don't like the form it's in to take a derivative, so I'm going to rewrite it as negative 4 minus x to the 1/2 power, right? Because that's a better form for us to be able to take a derivative. So if I work on my derivative here, it's going to be the 1/2 coming down, join in with the negative, negative 1/2. The group goes to 1 less power, 4 minus x. Now is at the negative 1/2 power. Don't forget the chain rule. Take the derivative of what's inside. That's a negative 1. Coefficient on the x. All right, if I make that better, prettier, negative negative makes it positive. I know I have a fraction. I have a negative exponent. Where's my 2? It's in the bottom. Where's my 4 minus x? It's in the bottom. What do I have on top? A whole lot of nothing, but there's a 1 placeholder. That is what your equation is for your slope. But now I want to know what it is at 2. So really what I'm looking for is f prime, what it is, yeah, 2. F prime of 2. This is going to get me the real slope, the number slope. So I will have, if I put a 2 in here, 1 over the square root of 2 times 2. So it's 1 over 2 square roots of 2. That's my slope. Here comes my equation of my tangent line, putting that together. Point up here. Let me circle my pieces. Here's my point. Here's my slope. And I'm going to take those things and put them into my equation. So y minus, actually plus, the square root of 2 equals 1 over 2 square roots of 2. And then I've got x minus 2. Now, Mr. AP is different than most math policemen in that he lets you keep square roots in the denominator. A lot of times you're supposed to rationalize that out, but Mr. AP says, it's okay. So we're going to leave it that way. We're not done the problem for part A though, because they want us to figure out what it would approximate for if the x value were 1.9. So what you're going to do is plug a 1.9 right in here. And now I'm going to go into box number 6 because I'm running out of space. So you're going to have y plus the square root of 2 equals 1 over 2 square roots of 2, and then 1.9 minus 2. And you're going to go to your handy dandy calculator. Maybe you might want to say this is a negative 0.1, but it's going to be a hot mess anyway, putting it in there. So if you take and put that in your calculator and calculate it out for sake of time, I'll tell you that it comes out to be negative 1.4495. You can check it out and make sure that's right. Is it an underestimate or an overestimate? Go back up to the top of the problem. It is concave up. Concave up's a happy face. Tangent lines are below. Therefore, it is an underestimate. Explain. Because f of x is concave up. That's number 5. And the last one I want to do is number 9 because I find it to be really goofy. It's one of your test prep questions, and I think it's a little bit, I don't know that you would get it in the way that it's worded and such. So don't want you stressing. Here we go. Let f be the function, 3x squared minus 4x plus 2. The tangent line to the graph of f at x equals 1 is used to approximate values. Isn't that what we've been doing this whole section? Using the tangent line to approximate values? Which of the following is the smallest value of x for which the error resulting from this tangent line approximation is more than 0.5? Now he said use a calculator, create a table to compare the values of the two functions, but I kind of thought of it more algebraically. So I'm going to take all my algebra route. I want to figure out what the tangent line is. So I need a point. You can't see me. I need a point, and I need a slope. I'm going to treat it just like the rest of them. If I want to know what it is at x equals 1, they're talking about 1. So my point is 1 something. Well, let's go here and plug a 1 in. 3 times 1 squared minus 4 times 1 plus 2. And guess what pops out? Lo and behold, a 1. Point is 1, 1. And then I say, okay, well, we need the slope. So the slope is now the derivative. Well, let's go derivativing over here. F prime of x would be 6x minus 4. What's the x value I'm concerned with? It's 1. If I plug a 1 in here, f prime of 1 equals 6 minus 4 is 2. My slope is 2. Can you put that together to get an equation of a tangent line? Yes, you can. Y minus 1 equals 2 times x minus 1. All right, so for this one, they want me to have an approximation that is more than 0.5. So I've got my tangent line. Let me keep going. I'm going to put my tangent line into an y equals mx plus b kind of thing. Y minus 1 equals 2x minus 2. Or y equals 2x minus 1. All right, so if I take this thing, now this is kind of just where my brain went with it. If I take this thing and set it equal to 0, take this value, 0 equals 2x minus 1. Then I solve for x. I get an x value of 1/2, right? An x value of 1/2. Well, what was my x value originally? My x value was original x. Can you not see me anymore, right? And the original x is 1. So if I can go a value of 1/2 away, 1 plus 1/2 is 1 and 1/2, and that is my answer of C. So I don't know. There's a lot of different ways you could do it. He gave you the hint to use the calculator and create tables. I kind of thought of it more along the algebra route, and that's where my brain went. So that's it, section 4.6. I will be in touch, but shoot me an email if you've got any questions, and I'll see you in class.